So last time we started talking about limits more rigorously, including doing some proofs. Today at the start, I want to illustrate why that's important. To illustrate that when you approach limits intuitively, sometimes you can get into trouble. And I want to illustrate that with the following example. We want to find the limit as x goes to 0 of the square root of x squared plus 9 minus 3, all divided by x squared. Okay, so it is kind of complicated looking. You might wonder, does the limit exist or not? And if it does exist, can we find it? And probably the first thing most of you would do, and I would agree with you, is you'd probably reach for your calculator, your technology, and see if that's helpful. Let's go ahead and do that. So I got my TI graphing calculator here. Found out right before class that this is not working in the most ideal way, but let's see what happens anyway. I'll go to my y equals screen. I do have the function plugged in already. You can plug it in yourself on your calculator if you want right now. Notice that I'm using parentheses to help specify that that entire numerator needs to get divided by x squared. So I'm using parentheses like you see there. And to play it safe, I also use parentheses on the bottom. We're letting x go to 0, so we want to plot this near 0. Okay, let's pick an ordinary window first. -5 to 5. And maybe -5 to 5 in the y direction because we're unsure what's going to happen. Let's just see what happens. Here comes the graph. Looks like it's a horizontal line. That's not very interesting. All right, well, let's zoom in a little closer. Is it really a horizontal line? Actually, let's change this to 0.5, say. It's actually not a horizontal line. Appearances can be deceiving. That's the first lesson. It's not a horizontal line. It looks like, even though this function is undefined at x equals 0, that there's probably a removable discontinuity there because we don't see anything that looks like a vertical asymptote. What is the limit? We could try tracing. When x is close to 0 but not equal to 0, what is y getting close to? It appears to be getting close to 0.16, a bunch of sixes perhaps, 0.16 repeating. If you know your fraction to decimal conversions, maybe it's 1/6. All right, let's see what happens if we zoom in even closer, like -1 to 1. And maybe I'll make this 0.2 and make these tick marks 0.05 apart in the y direction. There it is. Try to trace again. Yeah, it looks like it's getting close to 0.16, perhaps with the sixes repeating. Let's go in even closer for feeling less sure. Oh, how about really close? How about -0.10001 to +0.00001. Make my tick marks 0.000001 apart. And what happens? Some weird looking kind of stuff is happening. What in the world's going on there? And then there's even a big space. Is that the removable discontinuity? Well, remember, your calculator is just a dumb machine. It doesn't really know when there's a removable discontinuity and when there's not. Let's try Mathematica and see what Mathematica produces. Maybe Mathematica is a little bit smarter than the calculator. First of all, first lesson in Mathematica, how do you enter this function? You can give it a name like f, so I'm typing an f here. For Mathematica inputs, you use square brackets, not parentheses. That's the next lesson. Use square brackets, not parentheses. You might want to write this down. Then you put your variable name in an underscore. You can do an equal sign next. I, out of habit, do colon equals, which is fine. I'm setting my function equal to something, some formula. I'm about to type a fraction that I can get with what's called a palette. If you want to rewatch this part of the video, you can. This is called the palettes menu up there. I usually use the writing assistant palette. And there it is. It's kind of small. You can make it bigger. And in this writing assistant palette, for example, down here under typesetting, I see a fraction button. I just click the fraction button there. I also see a square root button. That's kind of nice. X squared plus 9, tab over, subtract 3, and then divide by x squared, just like you'd type it into a calculator. To enter this function into Mathematicus memory, I now do a shift return. Write that down, shift return. It'd be good for you to practice this and try it after class. Download and install Mathematica if you haven't done so yet. I just did a shift return there. You see something show up. It says in 208 there. You would not see it show up that way for you. You would see it show up in 1 because that would be your first input. There's my 208th input for this particular session. I want to plot this. So the basic command is plot with a capital P. Square brackets, function name, no underscore after the variable this time, comma, oh, let's go close to 0. In curly braces, put x comma negative 0.00001 to positive 0.00001, like we did with the calculator. And let's see what we see. This will give us a plot on this interval near 0. And what do we see? We see some craziness. Kind of like an infinitely oscillating function. Is it really oscillating infinitely often? It sure looks like it, doesn't it? And the calculator seemed to be doing something funny, but it wasn't showing us exactly that. What's going on here? Mathematica, does this function have a limit as x approaches 0? I can type limit with a capital L square bracket. Capitalization is important if you haven't gotten that across, realized that yet. The function name, again, no underscore. You only use the underscore when you first define the function. Comma, x arrow. How did I make that arrow? I did a minus sign, then a greater than sign, and it magically morphed into an arrow. Fun, fun, fun. Minus sign, greater than sign, magically morphs into an arrow. 0. Mathematica, what's the limit? 1/6. What is an approximation for 1/6? 0.16 evidently repeating. Is that really repeating? Well, yes, there's 100 decimal places. Okay, it's only rounding at the very end. So what's the answer? What's going on here? This is illustrating that the technology can lead you astray. Why is this happening? Essentially, it's limitations of technology. That's why this is happening. The answer actually is 1/6, but the technology is making mistakes. Numerical error, it's called. It's trying to deal with differences of numbers that are really close together, giving us really tiny numbers divided by other really tiny numbers, and that's causing problems internally in the system, leading to bad graphs. The original simple graph is actually what's going on here, not what you see here. Yes, as we saw last week, there are functions that oscillate infinitely often, but this is not one of them. This is computer error. So what do we do? Can we confirm this by hand? You can, but it's a bit tricky. It takes a lot of trial and error to figure out this trick for the first time. Hey, do you remember back, I don't know, 8th grade? Your teacher said, oh, we don't like square roots in denominators. Make sure you rationalize the denominator. What, is that a problem? Is it like dividing by 0? Does math die? Does this explode when you divide by a square root? The answer is no. There's 2 reasons to rationalize the denominator here. One is it makes it easier to check answers. And a second reason is that, well, it's a useful skill to learn. We will apply the skill up here, although we'll actually rationalize the numerator because the square root's in the numerator instead. You multiply this by a disguised form of 1. On the bottom, square root of 2 times itself is 2. On the top, you get a square root of 2. 1 over square root of 2 and square root of 2 over 2 are the exact same number. About 0.7 something. 0.707, I think, but they're different forms of the same number. You can use a similar trick here to help you evaluate this limit. That's the benefit of the trick, of knowing a trick like this. We're going to try to rationalize the numerator, not the denominator, the top and not the bottom. There's no square root in the bottom. No need to rationalize that. But how? Should I multiply by square root of x squared plus 9 over square root of x squared plus 9? That's not quite good enough either, because it's not going to get rid of the square roots on the top, because you got a -3 there as well. Another extra little trick you have to use is to also multiply by a +3. And if I do it to the top, I have to do it to the bottom. This is a trick. Where do tricks come from? Are they just magically pulled out of thin air? No. They come from lots of trial and error. The first people to ever think about this probably thought about it for hours and hours, maybe days and days or weeks and weeks. And they finally hit upon a trick that worked. And I'm telling it to you in a few minutes here. Right? We can stand on the shoulders of giants and see further, because they've done hard things before us. And now we can learn how to do those hard things. Tricks of the trade. Does this really help it? It seems like it might make it worse. Well, you got to FOIL the top, right? You got the product of two binomials with two terms. First times first, square root of x squared plus 9 times itself. The square root goes away, giving you x squared plus 9. But wait, there's more. There's outside times outside. 3 times square root of x squared plus 9. The square root didn't go away, but because I put a plus sign there, the inside product is -3 times square root of x squared plus 9. The square roots cancel. Oh, this is a beautiful trick. The outside and inside terms cancel. I am effectively using the fact that when I multiply a minus b times a plus b, outside and inside cancels. I get a squared minus b squared in the end. I'm effectively using that, with the square root of x squared plus 9 being the a and 3 being the b. Yeah, outside and inside cancel. Last times last is a -9. Hey, how about that? The -9s are going to cancel too. Now on the bottom, we've still got a square root, and you might think, well, that's not so good. But it turns out not to matter. We will be able to evaluate this limit, it turns out. Because the x squares are going to divide out. Boom, boom. And then we're left with a limit of a function that, well, you're not dividing by 0 now if you plug in 0. Like magic. It was not obvious that that was going to happen. But we can now plug in 0 here. This is a continuous function at x equals 0. We'll get 1 over square root of 9 plus 3. Square root of 9 is 3. There we have it, 1/6. There's your final answer. There's an algebraic confirmation that the answer is 1/6. We're smarter than the computer, right? We can think creatively. Again, you know, artificial intelligence is programmed. It's programmed to do what it does. It does, quote unquote, learn, but it's making models of data. It's not. It had to be programmed to do that, though, okay? It can be trained with models of data, but it doesn't mean it can think like you can, okay? Humans can make use of artificial intelligence as a tool, just like we use other kinds of technology as a tool. Doesn't mean it's necessarily going to lead to good things, I am concerned, but it is the way the world is right now. Does this kind of trick of rationalizing the numerator in this kind of case always work? Well, no, it depends, but the kinds of problems we give you, it typically does work. We should justify each step. Why is that equation okay? Because this is a big disguised form of 1, that's why. As long as I'm not dividing by 0, which I wouldn't be for real numbers x here, that's just a 1. It's not changing this function wherever this function is defined. Now this function, my original function, is undefined at x equals 0. But as long as x is not 0, this is a fine calculation, and it simplifies ultimately to that, as long as x is not 0. These two things are equal as long as x is not 0. So if this one has a limit as x approaches 0, so will this one, because they're the same. And remember, with limits of this kind, it doesn't technically matter what happens at x equals 0. All that matters is what happens as x gets closer and closer to 0 without actually equaling it. Though in the end, we plug in 0 because this function is defined and continuous at 0. If I graph this function on my calculator, the graph would look the exact same as the graph of this one, as far as the calculator is concerned, as far as what you can see on the calculator, or Mathematica for that matter, but they are technically different functions. This one is not defined at 0, this one is. This one has a removable discontinuity at 0, this one's continuous at 0. It fills in the hole. If I made this original one piecewise and said f of x equals that when x is not 0, and f of x equals 1/6 when x is 0, then they're the exact same function. I filled in the hole. That one's continuous. I can evaluate the limit by substitution. Get an answer of 1/6. I guess I forgot to mention that equality. That's just algebra. These are, again, equal for all x where they're defined. Really, this is probably the hardest equality to justify, because it is related to the fact that with limits, a limit like this as x goes to 0, it doesn't technically matter what happens at 0. It's a lot to think about, and you can't. And again, I've said this kind of thing before. You can't just sit here and say, yeah, I guess I get it, and then expect to get it really on an exam and do well on the problem related to this kind of thing. You have to think about it consistently to let it get it sink in, to think about what I said and try to apply those ideas, rethink about it. Question?
Just had a question about there's some questions.
If there's no plus or minus to the right, it's assumed to be two-sided. You're thinking about both directions, and you want the left-hand limit and the right-hand limit to be equal for the entire limit to be equal. When I do this calculation, effectively, I am imagining x approaches 0 from either the right or the left, and the calculation is still valid. So yeah, the main limits we think about are these two-sided limits where we don't put a plus or minus sign to the right of the number. If we do think about one-sided limits where we put a plus or minus sign to the right of the number, yes, that can be thought of, but sometimes just thinking about the two-sided limit is good enough. But we did see examples where the one-sided limits are different, like for the absolute value of x over x. And in those examples, the two-sided limit didn't exist because the one-sided limits were not equal. Here's another strange example. You know, we've looked at the example f of x equals, leave a little space in front of the sign here, sine of 1 over x if x is non-zero, and 0, for example, if x is 0, there would be a piecewise function. We've looked at this example already. This is the one that oscillates infinitely often near 0, and the amplitude stays at 1. We keep oscillating infinitely often between -1 and +1 as x approaches 0. Let me modify this a little bit. Let me just put an x in front of this. X times sine of 1 over x. I'll graph them both on the calculator. Well, let's graph just the plain old sine of 1 over x first. I'm writing it by hand as a piecewise function. Of course, I can't really type it in that way in the calculator. I need to imagine that I've typed it in that way. I'm plotting it near 0. Let's go out a little bit first. I'd want y to go from -1 to 1 as we saw before. This is just sort of hinting at the possibility of infinitely many oscillations. It's not proving it, though it's making it more plausible the closer we go into 0, because the oscillations seem to get wilder and wilder. Why is it oscillating infinitely often? It's effectively because the 1 over x, as x goes to 0, 1 over x if x is positive, say, 1 over x going off to infinity as x goes to 0. The inputs of this are getting arbitrarily large as x goes to 0. So I got sine of inputs the inputs themselves getting arbitrarily large as x goes to 0. Therefore, the sign's got to go through infinitely many oscillations. That's the intuition behind what we see here. What does Mathematica produce on this? Mathematica produces a better looking graph, you might say, but it'll still oscillate infinitely often. By the way, you can take code and copy and paste it. Again, to enter the code, make sure your cursor is somewhere within this cell here and do a shift return. And there is what Mathematica is producing between negative 0.0001 and positive 0.00001. Might have said the wrong number of zeros there on one of those. It's looking like plenty of oscillations, and in fact, infinitely often. If I go further out, then I don't see quite as many. But it's pretty clear it's oscillating a lot. Really, it is infinitely often. All right, coming back to the example where I multiply by x now. Okay, I guess I can do it here. Now I'm taking this function that's going to oscillate infinitely often near 0, and I multiply it by x, it's still going to oscillate infinitely often near 0. Multiplying by x is not going to change that. But what it does do is it takes these oscillations that are going between -1 and 1 and squeezes them down to oscillate smaller and smaller as x goes to 0. So I've still got infinitely many oscillations there, but the amplitude's getting smaller and smaller as I go to 0. And that, if I make it, well, that's enough to make the limit exist as x goes to 0. What's the limit of this new function as x goes to 0? Let me write it by hand. The limit of this new function as x goes to 0 does exist, and it is 0. It is oscillating infinitely often, but those oscillations are getting smaller and smaller, small enough to say this limit is 0. And in fact, if I've defined the function to be piecewise like this, to say it equals 0 if x does equal 0, then in fact, I've also made it continuous. It's even continuous. Technically speaking, to prove that this limit is 0 involves another version of the squeeze theorem. We looked at the version of the squeeze theorem for sine of x all over x that crossed its horizontal asymptote infinitely often as x goes to infinity. There's a similar idea for a squeeze theorem here. This graph is stuck between the lines y equals x and y equals negative x. Why? Because the sine function itself, no matter what its input is always stuck between -1 and +1 for output. Sine of something, anything, any real number at least, is always between -1 and 1. So if I multiply it by x, the output's always between -x and x. Because these are simple functions that definitely go to 0 as x goes to 0, this function is squeezed towards 0 as well.